Thank you. Thanks, Peter, for the nice introduction, and my apologies for the long title. I'm gonna let me thank the organizers first for the invitation, and thanks to the audience for being here and listening to this talk. So this is a joint work with Kumar Morley. Okay, so let me start with some background. So if you have so let's just start with the Hodge structures and mixed Hodge structures. Recall what they are. If you have a smooth projective variety over the complex numbers on nth degree, its nth degree cohomology with the coefficients in C, you have the Hodge decomposition. So it decomposes as these spaces HPQs, P plus Q is N, and HPQ is HQP bar. So HPQ is in terms of differential forms, would be represented by closed differential forms of type PQ. And those are, they have PDZ, these DZs and QDZ bars. Now, okay, so this is called the Hodge decomposition, and it's functorial. So if I have a morphism between varieties, and then you look at the morphism that you get between the cohomologies, then those morphisms between these HNs are gonna respect the Hodge decompositions of the two varieties. Now you take this as a prototype of the, as sort of like a prototype, and you make this into an abstract definition. So a Hodge structure of weight N. So this is a rational Hodge structure, but everything here is going to be, all the structures are going to be rational. So I'm going to drop that word. But a Hodge structure of weight N is the following data. It's a finite dimensional rational vector space HQ, and then together with the decomposition of its complexification as the direct sum of spaces HPQs, where P plus Q is N, and HPQ and HQ bar are complex conjugates of each other. The weight here is N, and this P plus Q is N. Now, so the Hodge decomposition can be, instead of talking about Hodge decomposition, there's an equivalent way of, giving the same data. So the Hodge decomposition is equivalent. You can describe it in terms of a filtration, which is called the Hodge filtration. It's a finite decreasing filtration on the complexification that satisfies this property. And the passage between the two definitions is as follows. So going from the decomposition to the filtration, what you do is that you take your FP to be the direct sum of all these RSs, with R being at least P. So it's it's the direct sum of the components where the holomorphic degree is at least P. That would be FP. And then there's also a passage in the other direction, which I'll omit. Now, this was for smooth projective varieties over C, but Grothendieck expected that this picture should generalize to arbitrary complex varieties, and this was done in the Leon's PhD thesis. So the observation is the following: that see, if I have let's say X is a smooth projective curve. So this is sort of, we're moving into towards the mixed world, and that's where the varieties are no longer smooth or projective. Now, let's say X is a smooth projective curve over C. Take 2 points of X, and now we are interested in H1 of X minus these 2 points. Okay, so you're trying to generalize this picture of Hodge structures to open varieties, non-projective varieties. And so this would be an example of that. And suppose that you had the picture generalizes to the non-projective situation. So you're supposed to have some analog, some version of Hodge structure on now this H1. And everything is supposed to be functorial, blah, blah, blah. So now if you look at the Meyer-Vittori sequence, a part of that is going to read like this for cohomology. So you have a map from H1 of X, the projective thing, to the direct sum of H1 of singly punctured curves, P and Q removed. This being induced by the two inclusions. It's like sort of like a diagonal embedding. And then you have the map from here to here, which is just adding, the sum of the two maps induced by inclusion. And then from here to here, that's a connecting homomorphism. And then after that is 0 because H2 of an open thing, non-projective curve will be 0. Now, okay, so from this, you get this exact sequence. This is now, so I placed, this short exact sequence. The first thing here is this guy, which so you can identify H1 of X minus a single point with H1 of X itself via the natural map, and then the sequence, the sequence reads like this. Now this is now H1 of X squared, and then you're modding that out by the diagonal embedding of H1 of X, and then you get the sequence like this. And now see, H1 of X is something that has weight 1. Right? It's a Hodge structure of weight 1. This thing here is a weight 1 thing. And then this thing here is H2 of a smooth projective curve. That's a weight 2 thing. So now on this open curve, X minus 2 points, you see that there's like a weight 1, there's a weight, the weight 1 thing is sitting inside that, and then the quotient is something that has weight 2. So this hints that, if you want to define some generalization of Hodge theory for these, for non-projective situation, instead of talking about just a single weight, you want to have a weight filtration. This sort of motivates now the following definition due to Deline, that a mixed Hodge structure is the following data: a finite dimensional rational vector space MQ, an increasing filtration on this rational vector space, call it the rate filtration, and then a decreasing filtration, which we call the Hodge filtration, on the complexification of the rational vector space. So again, a rational vector space together with an increasing filtration, rate filtration on that vector space, and a decreasing filtration on the complexification, such that if you look at each of these, pieces of associated gradient, so GR n of MQ, which is Wn, modeled out by, so this is a W, not a V, modeled out by Wn minus 1 of MQ, this thing together with the filtration that is induced by the Hodge filtration. So to be precise, you define Fp of that to be the image of Fp of Wn, under the quotient. Now this thing together with this filtration on it should be a Hodge filtration of weight n. So for any n, you want this thing together with the induced filtration to be a Hodge structure of weight n. Okay, so this is a mixed Hodge structure, and then the Deline's theorem is that there's for every complex variety, no restriction whatsoever at all. For every complex variety, there's a natural mixed Hodge structure on nth degree cohomology of that variety with coefficients in Q. So the underlying rational vector space is this, and then complexification, you have the Hodge filtration, so on. Okay, now. Any question about the definition? So
can I ask a small question?
Of course, yeah.
How important is it up to this point that the vector space be defined over Q? It seems like defining it over R would be enough, but maybe
absolutely. Yeah, you're absolutely right. So you can talk about real mixed Hodge structures, and then the vector space is going to be defined over R.
Okay.
Yeah. So what I'm defining really is a rational mixed Hodge structure, but the whole talk is going to be on rational mixed Hodge structures and Hodge structures. But you're absolutely right. The definition makes sense with R as well.
Okay, thank you.
You could also, of course, talk about integral mixed Hodge structures and mixed Hodge structures. And in fact, here, there's an integral structure with coefficients in Z. But again, for the purpose of this talk, I really want to just work with the rational structures.
Okay.
Okay, so now, so these are mixed Hodge structures, and there's an obvious, sort of a notion of morphism for these objects. Morphism would be a linear map between the underlying rational vector spaces that respects both the weight and Hodge filtrations. And then you get a category.
Sorry, another small question. Every complex variety means every complex variety means they can be compact or not compact, smooth or not smooth, right? So you're
absolutely, yeah. So that was the whole point of leaving the pure world and going to the mixed world. Absolutely.
So you can be mixed for two reasons. You can be non-compact or you can be non-smooth.
Exactly. Yes, absolutely. Okay, now this way we get a category of mixed Hodge structures, and this category is an abelian category, which is interesting. So if you look at the category of filtered vector spaces, that's not an abelian category. But category of mixed Hodge structures, somehow because of having these two filtrations that are sort of working against each other, this is actually an abelian category. And then it actually, it has a tensor structure. So you tensor product everything, the tensor product the vector spaces and the two filtrations. There's a tensor structure, you have duals, and then there are internal harms. So if I have two, mixed Hodge structures, M and N, with, underlying vector spaces MQ and Q, then there's a mixed Hodge structure with the underlying vector space just being linear maps from MQ to MQ. That's the internal harm. So sort of like, representation theory, where, if you have two representations of a group, you also get an internal harm. On the linear maps between the two vector spaces, you also get a representation. So the situation is exactly like that. And this is actually relevant later on when we talk about this in a slightly more abstract frame. Okay, so let me go to the next slide. So now I want to talk a little bit about Mumford-Tate groups, sort of like a quick, recalling the definition, and also I want to motivate the definition too, just sort of to put things into better context. So suppose again that X is a smooth projective complex variety. Again, so I'm going back to the smooth and projective situation. Now, elements of, if you take an even degree cohomology with rational coefficients, and then the elements of that are of type PP, P comma P, so degree 2P, and the elements are of type P comma P, these are called Hodge classes of weight P. Now, so by ZP of X, I mean the space of algebraic cycles of codimension P on X with coefficients in Q. So this is by definition is the Q vector space on the set of irreducible Zariski closed subsets of X. Now, for every algebraic cycle, you have, there's a cohomology class assigned to that. So this class map going from codimension P algebraic cycles to degree 2P cohomology. So one way to think of it is that it's simply just, it's the Poincaré dual of integration over Z. Now, it's easy to see that one can see that this is the image of this class map actually lands inside inside this space here, the space of Hodge classes. So the classes will be defined over Q and they'll be of type P comma P. Now we're going to say a Hodge class, so an element here is algebraic if it's in the image of the class map. So if it's the class of some algebraic cycle. And then the Hodge conjecture predicts that every Hodge class should be algebraic. Now, a useful tool in attacking the Hodge conjecture has been the so-called Manfortade groups. So suppose H is a Hodge structure of weight 2P. So this could be, the H2P of a complex smooth projective variety. Now, the elements of the underlying rational, the elements that are defined over Q and are of type P comma P, these again, following previous definition, we call these Hodge classes of weight P for this abstract Hodge structure of weight P. And then this Mumford-Tate group of H is a group that we're going to talk about in a second. But the nice thing about this group is that it's sort of it really it characterizes it gives us a way to characterize all the Hodge classes in these tensor powers. So tensor powers of H with its dual. So something of this form, look at the direct sum of these things, and Hodge classes in this, these are captured exactly by this Mumford-Tate group. So what's the definition of this rule? So the Mumford-Tate group of H is the subgroup of GL of HQ, HQ being the underlying rational vector space, is the subgroup of that general linear group, which fixes, see, of course, general, this GL group, well, it acts on HQ, so it acts on each of these tensor powers. You can look at, underlying rational vector spaces, or you can extend their scalars. But, so this thing acts nationally on each of these things, and hence on direct sums of these things. And then you see the Mumford-Tate group of H is the subgroup which fixes all the Hodge classes of weight 0 in direct sums of such objects. Okay, so we get all the Hodge classes in these things, and then it's by definition the Mumford-Tate group of H is the subgroup of the general linear group that fixes all those Hodge classes of weight 0. I'm going to denote this Mumford-Tate group of H by G of H. And now there's some facts. I'm going to state some facts about this group. The first statement is the following. See, you define the Mumford-Tate group as the subgroup that fixes the Hodge classes of weight 0, right? But now the assertion is that every invariant of this, so if an element of the direct sum of these objects is fixed by the Mumford-Tate group, then that element is actually a Hodge class of weight 0. So the invariants of this are exactly your Hodge classes. So that's that sort of explains what I was trying to say here, that really captures these Hodge classes of weight 0. And then
sorry, Payman, just quick clarification. By invariant, you mean fixed point, right?
Fixed point, absolutely, yes. Yeah,
okay.
Absolutely fixed point. And just to be clear, so the invariants of them that are defined over Q. Okay, so you look at so you look at the action on the rational vector space, and all the invariants of that would be Hodge classes.
Okay, thank you.
Yeah, thank you. Great question.
So a small question. So to be because the weights are always non-negative, to be of weight 0 in that tensor product means your tensor product of weight zeros, right?
No. See, you also included the dual.
Okay. So I see.
Yeah, so that's really important. It's a great question. So you're looking at tensor powers of H and its dual.
Okay. Yeah. Then okay. Yeah. Then of course you can be much more. Okay.
Exactly. Yeah.
Okay.
So okay. Now, if your Hodge structure happens to be the nth degree cohomology of a smooth projective variety, then the Manfortade group is reductive. So that's because of because you have polarization. So you could use the polarization to show that that the Manfortade group is actually a reductive group in this case. Now, just again to motivate Manfortade groups, let me sort of to convince you that these are interesting objects. Let me give a quick application here. So the application is the following. You can prove fairly easily using Manfortade groups that the Hodge conjecture holds for powers of elliptic curves. So let's go over this. So suppose E is an elliptic curve over C, and the claim is that Hodge classes on e to the power of n are generated by elements in degree 2. So the Hodge classes are generated by H2 Hodge classes in H2 of this thing. And this gives the Hodge conjecture because by Lefschetz, Hodge conjecture holds in degree 2. And then once all your Hodge classes are generated by elements of degree 2, you get the Hodge conjecture in this case. Now the proof of this proposition goes as follows. So up to a certain point, I'm going to keep it general, but then I'm going to do it really, finish the proof only in the non-CM case. The CM case requires a little bit of more work, but again, it uses Mumford-Tate groups. So let's look at the Mumford-Tate group of H1 of the elliptic curve. And I'm going to just call that, Mumford-Tate group of the elliptic curve, G of E. So this is a subgroup of GL of H1 of E, and that's a two-dimensional vector space. So it's a subgroup of GL. You can identify it with GL2. And it's not hard to see that, so this is, you use some general, observations, and it's not hard to see using those that the Mumford-Tate group in this case, there are two possibilities. Either it's going to be the full GL2, or it's going to be a two-dimensional torus inside GL2. And it would depend which case you're in. It would depend on whether you have CM or not. If you don't have CM, if you don't have complex multiplication, the Manfortade group is going to be the full GL2. And if you do have CM, then the Manfortade group is going to be a two-dimensional torus. Now, we're interested in powers of the elliptic curve. So e to the power of some n, and look at the cohomology ring of that. Now, well, because that's an abelian variety, that's just the exterior algebra on H1 of that abelian variety, which would be H1 of E, 10 to the power of n. Now, so Hodge classes in here, see, we said that Hodge classes are exactly invariants of the Mumford-Tate group. So the Hodge classes in here are exactly the invariants under the action of the Mumford-Tate group of this exterior algebra. Now, in the non-CM case, where your Mumford-Tate group is just GL2, the proposition will amount to the following classical statement from invariant theory, that the subring of G, so if suppose V is any vector space, any rational vector space, the subring of GLV invariance of exterior algebra of V to the power of n is generated by elements in degree 2, by invariance in degree 2. And this will give you, this will imply that all Hodge classes in the situation, Hodge classes here, all of these things are invariants of this are generated by degree 2. In the non-CM case, it requires a little bit more work, but again, it's going to use the Mumford-Tate groups, and we get the Hodge conjecture in this case. Okay, so hopefully I've convinced you that Mumford-Tate groups are useful objects. There's also several conjectures, important conjectures in arithmetic geometry. They're sort of they are related to Mumford-Tate groups. And there's the, if you want to generalized Hodge conjecture that would involve Mumford-Tate groups. There's also Mumford-Tate conjecture. There's the motivic, there's Grothendieck's period conjecture. All those conjectures in one way or another are related to the Mumford-Tate groups. Okay, so far I've been talking about Mumford-Tate groups of a pure Hodge structure, Hodge structure of some weight, but in the mixed case, you could just use the exact same definition. So if I have a mixed Hodge structure M, you define its Mumford-Tate group, G of M, to be the subgroup of GL of the underlying rational vector space, which fixes all Hodge classes of weight 0 in the direct sums of these objects. So this guy here by definition means M. Take M. This is M tensor power M. I shouldn't have used M there. There are two M's, but hopefully my hand is pointing out to the right M here. So this by definition is M tensor M, tensored with M dual tensor M. So again, you're taking tensor powers of M and its dual. So Mumford-Tate group of M again is the subgroup that fixes all those Hodge classes. And then some useful interesting facts about this Mumford-Tate group is that, so first of all, morphisms are GM equivariant. They respect the action of the Mumford-Tate group. Again, just like in the pure case, every invariant is a Hodge class of weight 0. And if M is pure and polarizable, then GM is reductive. So this would be, this is why Mumford-Tate group of smooth projective varieties are reductive. More generally, M is a semi-simple object if and only if its Mumford-Tate group is reductive. Now, this talk is really not about semi-simple mixed Hodge structures. It's about the ones that are truly mixed, just to say that their Mumford-Tate group is not reductive. So I want to talk about the unipotent radical of the Mumford-Tate group a little bit now. The talk is really, it is about the unipotent radical. So the Mumford-Tate group of, so suppose M is a mixed Hodge structure. Now, because we said that the action of the Manfortade group respects morphisms, in particular, it's going to respect the weight filtration. So this is going to be contained in the subgroup of GL of M, which respects the weight filtration. So this is the parabolic subgroup of GL associated to the weight filtration. I'm going to denote that by G naught of M. If you take a suitable basis, if you take a basis compatible with the weight filtration, then this would be just the space of upper triangle, invertible upper triangle, block upper triangular matrices that look like that. And then inside this, you have its unipotent radical, the unipotent radical of G naught. This is now the elements of G naught, so elements that preserve the weight filtration and induce identity on the associated gradient. So thinking in terms of matrices, after we take suitable bases, this is going to be now block upper triangular with ones on the diagonal. Now we take the intersection of GM with U naught, and we denote that by U of M. Now this talk is about U of M. So let's try to remember the definition. So it's the intersection of the Manfortade group with the elements of GL with these elements of GL. Now we have a diagram like this. G sits inside G naught, and then this is these upper triangular matrices, invertible matrices, and then by restricting to the diagonal, you get a map into the product of GLs of these associated graded parts. And then inside this, you have the Mumford-Tate group of the associated graded of M, and then this map factors through that, and then this is the kernel of this, the diagonals being 1, and this is the kernel of and this one will be the kernel of this one. Now, the reason I have this diagram here is partly because, see, if the associated gradient of M is semi-simple, then this would be reductive, and this being a unipotent group because it sits inside this U naught, then this UM is going to be the unipotent radical of GM. So when your associated gradient is semi-simple, then this UM is really the unipotent radical of GM. And by the way, in the examples that you're interested in, examples that we're interested in come from geometry, the associated gradient will always be semi-simple. So in general, if you have Hodge structures, mixed Hodge structures that come from geometry, their associated gradient is always semi-simple. Category of pure motives is semi-simple category. So in general, we're going to say U of M is large if, UM is contained in this U naught, in this subgroup, and we're going to say UM is large if it's actually equal to U naught. So it's as large as it can be. And any question about this slide, this definition?
So just in terms of basic direction, you are trying to measure the extent to which a mixed Hodge structure is semi-simple by looking at its Mumford-Tate group and saying, is the unipotent radical, trivial, for example, or something.
Exactly. The unipotent radical is trivial, it'd be semi-simple. The larger it is, in some sense, this is farther from being a semi-simple object.
Okay.
Exactly.
Okay.
And we say the unipotent radical is large if it's as large as it can be. So you've got this sort of trivial, upper bound for it, and we say it's large if it's equal to that upper bound.
Okay. And so if it is large, then you're saying it's sort of as far as the mixed Hodge structure is like as far as possible from being semi-simple.
Exactly.
Okay.
Yeah, exactly. Okay, so the question is the following: that do most mixed Hodge structures have a large unipotent radical? And this is what this talk is about. And so when you want to do this, it's natural to fix the associated gradient, of course. Right? So going back to the sequence here, what we want to do is that fix the associated gradient of M. Now this will be fixed, and now it starts varying M. and then see, you know, how often this thing is going to be large. Now, so that brings us to the next section here. So I'll talk about mixed Hodge structures which have a fixed associated gradient. Family of mixed Hodge structures with a fixed associated gradient. So let's fix the following data. You fix a rational vector space. So what I want to do is that, you know, I want to fix the underlying rational vector space. I want to fix the weight filtration on that rational vector space. I also want to fix the associated graded Hodge structure. And now let the actual mixed Hodge structure vary. That's what we wanted. All right, so we fix an underlying rational vector space, fix the rational vector space in Q, and increasing filtration W on it. And for each n, fix a Hodge structure of weight n on this associated gradient. Let's call that m tilde n, and take the direct sum of all these m tilde n's, call that m tilde. So this is now this is a Hodge structure on the associated gradient of m, and on the nth degree piece, it's going to have weight n exactly. And we'll say a mixed Hodge structure m. See, my notation might be a little, maybe it's not the best. The point is that, see here at this stage, there's no m's yet. You just have this rational vector space MQ. But now we're going to say a mixed Hodge structure M is associated to this triple. Let's call it mu, the triple being exactly this data here, MQ, weight filtration, and m tilde, the Hodge structure on the associated gradient. We'll say M is a mixed Hodge structure associated to this triple if, well, its rational vector space is MQ, its weight filtration is W, and its associated gradient is exactly the m tilde that we fixed. Yeah, now, so any such M, well, it's determined by its Hodge filtration because you fix its rational vector space and the weight filtration. The only thing that is left to play with is the Hodge filtration. So you get an injection from the set of mixed Hodge structures associated to this triple mu to the complex points of the flag variety of MC with suitable, dimensions. But by just going, sending to the Hodge filtration. And then if you take a filtration, if you take an element here, let's call it F, this would be a mixed Hodge structure associated to mu if and only if the filtration that this induces on the associated gradient is exactly the Hodge filtration on m tilde, the one Hodge filtration that you fixed on the associated gradient. Right? So the point is that you fix the Hodge filtration on the associated gradient. That's giving you a Hodge structure. And now you're looking at the filtrations on M itself, on MC itself, which give you that filtration on the associated gradient. Now, the parameterizing the space of all mixed Hodge structures. See, I want to look at the parameterizing space of all the mixed Hodge structures attached to a triple, the triple mu. See, in general, if you only fix the rational vector space and the weight filtration, and you fix the Hodge numbers, okay? So fix the rational vector space, the weight filtration, and the Hodge numbers, the parameterizing the space you're going to get, that's not going to be an algebraic subset of the flag variety. Because you have to worry about complex conjugation, right? Because your Hodge filtrations have to satisfy, behave nicely with respect to complex conjugation. And because of that, this won't be an algebraic subset. However, once you fix the associated gradient, now the space of mixed Hodge structures attached to the triple mu, this is actually an algebraic subset of the flag variety. So more precise statement following that there's an affine, and it's affine. This is really important. There's an affine complex variety denoted by S of mu being our triple. With a canonical bijection between the complex points of that affine variety and the set of all mixed Hodge structures associated to the triple mu. Even better than that, this affine variety is actually it's an affine space. It's isomorphic to some AN. Again, so this is happening because you fixed the associated gradient. That's the key thing here. See, so I mean, just a comment about how this is proved. So the proof is easy. What ends up happening is that this S of mu will be a homogeneous space quotient of a unipotent group. And the reason this is unipotent is exactly because you fix the filtration, the Hodge filtration on the associated gradient. Because of that, this is a quotient of a unipotent group by subgroup of it. And then, by an old theorem of Rosenlicht, all these quotients of a unit. I was going to say old theorem of Rosenlicht, but I think all theorems of Rosenlicht are fairly old. But by a theorem of Rosenlicht, all quotients of a unipotent group by a subgroup are isomorphic to affine spaces. They're in the characteristic 0. So, okay, so that's how you get that these are affine spaces. And the key thing is that you fix the Hodge filtration on the associated gradient. And then just for notation, for later purposes, if you take a point S in this parameterizing space, so you have a mixed Hodge structure, at S on the triple, and I'm going to denote that by M sub S. So this is the corresponding mixed Hodge structure associated to the triple, at the point S. Okay, so going back to the question that we had, are most mixed Hodge structures, do most mixed Hodge structures have a large unipotent radical? So this is the result. This is the answer to that question. So this is with Kumar. That so let mu be a triple as above. And suppose, so you have to assume two conditions here. One, that M tilde is semi-simple. So M tilde is the Hodge structure on the associated gradient. So this being semi-simple, that's a very reasonable condition. It will hold if you're interested in geometric situations. This will always hold. You don't have to worry about this. But the second condition is that M tilde satisfies some conditions, some technical condition. I'm going to say something about it here. I'll tell you exactly what it is. But it's something that we call an independence axiom, but some technical condition. Assuming that these two conditions hold, then the Mumford-Tate group of a very general mixed Hodge structure attached to mu has a large unipotent radical. So in other words, outside a countable union of proper Zariski closed subsets, the unipotent radical is going to be large. So instead of so outside a union of countable union of proper Zariski closed subset of S mu, outside of that, the unipotent radical is going to be large. So the answer to the question that I posed earlier is that yes. And most meaning very general there. Now, something about this technical condition, the independence axiom. So precisely the statement we need is the following, that if you look at the internal harms of these so remember M tilde is graded, right? So you look at the objects, these objects, so the internal harms of M tilde j, comma, M tilde I. So that's the same as the dual of M tilde j tensored with M tilde I, with I less than j. So you're looking at the ones that give you, negative weight for this. Okay, the requirement is that these objects for different pairs I comma j, they don't have any non-zero isomorphic sub-objects. That's the requirement that we need. Now, one thing I'm going to say is that most likely, the assertion here remains true if you remove probably both of these conditions, at least condition 2. If you remove that, mostly this is going to remain true, but our proof does need condition 2. And I hope that by the end of this talk, I'll be able to tell you why our proof needs this condition. So the plan for the rest of the talk is the following. I'm gonna go back and go over some more background on Mumford-Tate groups, and in particular, we're gonna go over the things that the background that we need in order to prove this, to go in the proof, and then hopefully when I'm doing that, you'll also see why our proof. Well, I'll make some indications for why our proof needs this independence axiom. And then we'll also, hopefully, if you have time, we'll also do a quick overview of the proof. Okay, so let's talk about Manfortade groups again.
Just a quick question.
Yes, yes, yes.
You said the first hypothesis was fairly reasonable. Anything coming from geometry is going to satisfy that. We're happy. How reasonable is the second assumption?
See, okay, so the second assumption really depends. It depends on your associated gradient, the associated gradient that you fixed, right? Many pure motives, Hodge structures will satisfy that. Many won't.
Okay. So it is restrictive. I mean, there are things that do not, yeah.
Right, yeah, and our proof really needs it because we're using the result that is only true with the hypothesis. So the machinery that we use to prove this, that machinery fails if you don't have this this hypothesis, and it is restricted. Yeah, but a lot of in many cases it holds, but it is definitely restrictive.
Sure. Thank you. Thanks.
No problem. Thank you. Okay, so going back to Mumford-Tate groups. So the definition that I gave earlier about Mumford-Tate groups, that was in terms of invariance, in terms of fixing Hodge classes. But there's sort of a more natural way of defining Mumford-Tate groups, more abstract, but also more natural, and that's in terms of Tanakin formulas. So remember, we pointed out that the category of mixed Hodge structures is abelian, there's tensor structure, you have duals, and also there's this extra, also double duals are isomorphic to the object itself. I didn't mention it, but this also holds. And there's also this other technical condition here. So the endomorphisms of the unit object. Okay, so there's a tensor structure, there's a unit object for that tensor structure, and the endomorphisms of that unit object are just Q. By the way, the unit object is simply the rational vector space Q sitting in weight 0 and F0, sitting in weight 0 and the Hodge filtration 0. If you're thinking in terms of geometry, this would be like H0 of a point. Now, okay, so you have category of mixed Hodge structure satisfy these properties, and then by sending a mixed Hodge structure to its underlying rational vector space, you get a functor from mixed Hodge structures to vector spaces over Q, which is exact, it's Q linear, it's faithful, and it respects the tensor product. Now, all of these things together, they say that category of mixed Hodge structures is a Tanakin category over Q. And this, the forgetful functor is a fiber functor. Now, by definition, a Tanakin category is a category that satisfies these conditions here, for which there is a fiber functor. And it's sort of prototype example of a Tanakin category is the category of finite dimensional representations of a group or a group scheme. Now, the fundamental theorem of this theory is the following theorem due to Saavedra-Divano, and then so it's originally due to Saavedra-Divano, but there was like a bug in that theory in the argument, which Deline and Milne fixed later on. The result is the following: that actually every Tanakin category over Q is equivalent to the category of finite dimensional representations of an affine group scheme over Q. So all Tanakin categories are category of representations. And in fact, it's more precise than this. It really tells you what the group is. So going back, to the category of mixed Hodge structures in Mumford-Tate groups. So suppose M is a mixed Hodge structure. Let's look at the Tanakin category generated by M. So this is the smallest full Tanakin subcategory of the category of mixed Hodge structures that contains M, the unit objects, and is closed undertaking sub-objects. So essentially, it's obtained by including M, the unit objects, and then making it closed under direct sums, tensor products, duals, and subquotients. Now, okay, so this is now itself a Tanakin category, and then via the fundamental theorem, this is equivalent to the category of representations of some affine group scheme. So more precisely, what we get from Tanakin formalism is a group scheme GM. I'm going to denote that by GM. I'm not using my notation because GM was defined in a different way earlier. but it ends up being the same thing. So, so please forgive me. But there's a group scheme. It's called GM over Q, and together with the natural action of this GM on every, so for any object X of this subcategory, this guy naturally acts on the rational vector, underlying rational vector space of the object. So every object now becomes a representation of this, and then these actions are compatible with the morphisms. You get a functor from this category to the category of representations of GM, and this is actually an equivalence of categories. And so this GM is well, the new definition is that this group, we call it the Mumford-Tate group. And the theorem, the claim is that the two definitions of the Manfortade group that we've given, they are actually equivalent to each other. Now, going back here, see, so far I've said that this is an affine group scheme over Q, but see, okay, so GM, in particular, by looking at how it acts on M itself, so on the representation associated to M, you get a map from GM into GL of MQ. And because this category is generated by M, the action on every object is determined by how it acts by the action on M. So this is actually going to be an inclusion. It's going to be an injection. And this way you identify the GM as a subgroup of the general linear. But that's a more, I think, more conceptual way of thinking about the Mumford-Tate group. Now, going back to UM, which is really the object of study, or object of interest in this talk. So how do we go about describing UM? Okay, again, let M be any mixed Hodge structure. Remember this diagram that we had earlier. So this is the Manfortade group of M sitting inside. This is the parabolic subgroup, these upper triangular ones, taking bases appropriately. These are the ones that respect the rate filtration, and this is the unipotent radical of that, and that's UM. Now, little um, lowercase um, be the Lie algebra of the group UM. Okay, so now this sits inside the Lie algebra of U naught M. The Lie algebra of U naught N, so U naught N is, you know, things of this form. And then, so the Lie algebra of that is going to be the endomorphisms, strictly upper triangular endomorphisms. Or in other words, it's the, to be more precise, it's the endomorphisms of the underlying rational vector space, which drop the rate filtration by 1. So they send Wn to Wn minus 1. And I'm going to call this thing W minus 1 of N M. So UM is a sub-Lie algebra of this thing. Now, if you look at the adjoint representation, the adjoint action of the adjoint representation of GM. So GM acts on itself by conjugation. You look at what happens to the Lie algebra, and this being a normal subgroup, that action restricts to an action of GM on the Lie algebra of UM, on little UM. And then via Tanakin formalism, anytime you have a representation of GM, you get a mixed Hodge structure. So this gives you a mixed Hodge structure, which I'm going to denote by underlying UM, whose underlying rational vector space is just the Lie algebra UM. And what happens is the following. So this thing here now underlies a rational vector, underlies a mixed Hodge structure. This guy here also underlies a mixed Hodge structure. So this would be the mixed Hodge structure that is W minus 1 of it's W minus 1 of NM, and being the internal So this is a mixed Hodge structure whose underlying vector space is this W minus 1 and M. Those are strictly upper triangular matrices. And then by thinking about how, you know, the two actions that you have corresponding to this and this, it's easy to see that this thing is actually, this U underlying U is actually a sub-object. It's a mixed Hodge substructure of W minus 1 and M. And now going back to, what the definition that we had, we said that the unipotent radical is large, but definition was that if and only if it was equal to U naught. And then, well, these are unipotent groups, so that's the same as the Lie algebras being the same, and that would be the same as saying that that UM is the same as W minus 1 and M. So during the talk, I have the underlines in my writing, but I'll just refer to this as UM. I won't keep saying underline. Okay, so UM being large is the same as the little UM being the same as this W minus 1 and M. Okay, so now the question of characterizing this guy now amounts to characterization of this guy because you're dealing with unipotent groups. So how do we do that? Okay, so for any integer p, we have this extension coming from the weight filtration on the p part of the weight filtration of M. So I'm going to denote it by EPM. This is given by the inclusion of WPM into M and then going to the quotient. Now, this guy, okay, so it's an element of the X group. So these are unit X groups. It's an element of the extension of M mod WP by WP. And then, you have these canonical isomorphisms, just like you have, in linear algebra, but you can, just like you have for modules, you can take this guy from here, you move it to the, to the second variable, you replace it by its dual. And that's the same as on orders, this is canonical isomorphic extensions of the unit object by the internal harm, now this comma this. That's the same as saying that, the dual of this tensors with this. And then, see, you have a natural inclusion. You can think of this internal harm as being naturally a sub-object of this W minus 1 and M. So, you can ignore, just to sort of simplify things, you can ignore the underlines and just think about these things as linear maps between the underlying rational vector spaces. Yeah. So now if I have a linear map from M mod WP to WP, well, that would naturally give me a linear map from M to M. Namely, I start with M, I go to the quotient, then I pass here, and then I go back to M by just inclusion. So this guy here naturally injects to end M, right, without the W minus 1, but because, the weights are dropping because of, the way things are over there, it really maps into W minus 1 and M. So you get an inclusion of this guy into here. And then by functoriality, you get a map from this X group to this X group, which will normally these maps are not going to be, necessarily injective, but here, they will be injective because some weight consideration. So you get an injection of this X group into this X group. Now, okay, so now for any integer p, I have this EPM, an element here, which you can think of it as an element there. But now think of it as an element here. Now all these EPs live in the same space, and now you can add them up there. So by E of M, or total extension class of M, I mean the sum of these EPMs over all P as an element of this X group. Okay, so now the picture looks like this, that this E of M is an extension of 1 by, going back here, is an extension of 1 by W minus 1 and M, 1 by W minus 1 and M. And inside this, you have UM. And the question is, well, what is UM? And now there's a theorem of Deligne that says the following, that UM is the smallest sub-object of W minus 1 and M, such that the push forward of EM, the push forward of this extension, along the quotient map by UM. So you have the quotient map from here to W minus 1 and M, modded out by UM, and you're looking at the push forward of this extension along that quotient map. And the claim is that UM is the smallest sub-object such that that push forward is trivial, that push forward splits. So to be more precise, for any sub-object A of W minus 1 and M, the push forward of EM under the quotient map by A, that's what I mean by this, splits if and only if A contains UM. So this class of M, this total class of M characterizes UM, the Lie algebra of the unipotent radical. Now, this push forward is nothing mysterious, right? So the point is that if I write my extension EM, well, it's after all extension of 1 by this W minus 1 and M. So forget about the purple things for a second. This EM is after all extension of 1 by this W minus 1 and M. There's some object in the middle. I don't want to, it doesn't matter right now what it is explicitly, but some object in the middle. And then the push forward, when you mod out this out by A, all you're doing is that you're modding out this guy and this guy by A. And then, so the claim is that, this thing would split if and only if A contains UM. And then the remark, a simple observation, but useful, very useful, is the following, that see, because here you have something that only has negative weights, and here you have the unit object. This extension splitting is the same as saying that this object in the middle has a non-zero Hodge class of weight 0. These two statements are equivalent to each other. The extension is splitting, and this object in the middle having a non-zero Hodge class of weight 0. And then, well, the question is the following, that do you have something similar to this for the individual classes EPM? Peter, how much more time do I have? I know it started a little late, but how much more time do I have?
4 to 5 minutes.
4 to 5 minutes. Okay, so I'm going to go a little faster. I'm going to skip some things. Okay, so the question is, what can you say about these individual classes EPs? I know, it's easy to see that these push forwards, put EP modded out by UM, these things don't have to split in general. But what you could do is the following. You can still extract some information. So the point is that if you take UM and intersect it with this sub-object of W minus 1 and M. So thinking these are the maps that vanish on WP and whose image is contained in WP. And I intersect this with that, I'm going to call this UP. And if I write EPM, okay, it's an extension of 1 by this internal hom, and UP is sitting inside here. Now, and there's some object here in the middle. And the result is that, so this is joint with Kumar, but it really, it's already, the proof is already, it's already exists in a work of Charlotte Erdogan, and also that work, it builds on a result of Bertrand. But the fact is that for any, so the UP is the smallest sub-object of this internal hom, such that the quotient of this by UP belongs to this subcategory. So for any object A of that, A contains UP if and only if this quotient belongs to the subcategory. Now this is sort of an ugly result, I want to call it, because it's a characterization, but I mean, it's hard to decide if something belongs to the subcategory or not. But now one has the following result. That suppose that the associated gradient of M is semi-simple and an independence axiom. So this is something that has a very, it's a very similar, it's got a very similar flavor than the independence axiom that showed up in the original theorem that was stated first. And suppose that some independence axiom holds. Then the statement here greatly simplifies. What you get is that UP will actually be the smallest. UP will be the smallest sub-object of this, such that the quotient of this by UP splits. So this, this ugly thing being in the subcategory, blah, 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 greatly simplifies, simply becomes the statement that, for any sub-object A contains UP if and only if this quotient, this extension splits. And now again, splitting amounts to existence of non-zero Hodge classes in the quotient of this thing by, by A, whatever A you have. Now, I know I'm almost out of time, so I'll just take 1 minute to say that, see, going back to the statement of theorem that, I stated first, I stated this, this independence axiom. The reason we need it is because we use this theorem here. So we get stuck in trying to use the Lean's theorem. What happens is that, what you're going to do is that you look at quotients of this by A, by various A's, and by this condition here, you want to see, when you have non-zero Hodge classes. And then, you can show that The sets where an element becomes a Hodge class is going to be Zariski closed subsets. So this would be analog of Katani, Deline, Kaplan's result. But then you get these Zariski closed subsets, but then you want to have to show that they are proper, and we can't do it when we're trying to use this extension. When we're trying to use the total class, we can't do it. It becomes too complicated. But when you use this, then we can get the properness as well there. So that's why we can, we have that independence axiom, because we use this theorem here instead of Deline's. And this theorem really does need the independence axiom, because the conclusion is false if you don't, in general, the conclusion is false without this hypothesis here. So I'll stop here. I know, yeah.